Okay, so this is joint work with Gorjan Alagic, Stacy Jeffrey, and Maris Ozos. So modern crypto is a very diverse field, as we all know. So we talk about post-quantum crypto, where we consider classical crypto systems, but we imagine that there are quantum adversaries out there who might have a quantum computer in their garage, and they might listen to a classical channel, and in the case of RSA, say they might factor a large integer, for example. But then on the other hand, we also have fully quantum crypto, where everything is quantum, right? Encryption and decryption are now quantum operations, and we think of quantum channels that transmit quantum information or quantum states. So in the future, I guess we expect to see more and more quantum devices out there. Will this make classical cryptography obsolete? Well, probably not. But in any case, it would be important to understand how secure classical crypto really is in a quantum world. And one model to consider is not only the quantum adversary that kind of listens to a classical channel, but also the quantum adversary that actually has superposition access to this classical crypto system, okay? I mean, we know that encryption and decryption are efficiently computable functions. So in principle, one could implement those on a quantum computer and ask if this has any consequences for the security. Okay, and in this talk, we'll look at this kind of model, which is often called something like classical cryptography in a quantum world, which was coined by Bonnet and Jandry. And I'll try to convince you that there's a particular interesting security definition that one could consider that has really interesting applications. Okay? So let's talk about what security in a quantum world means. So we have some intuitive ideas on what it means, right? I mean, we have a notion of indistinguishability, right? We want ciphertext to reveal no information about the plaintext, and we want ciphertext to somehow all look indistinguishable from another. And of course, now we have to work under the assumption that adversaries are quantum, and if they take reasonable amounts of time for their attack, then we assume that they run in quantum polynomial time. Okay, so I was mentioning indistinguishability. Let's try to formalize this in a kind of game. So this is the int game between a quantum adversary and a classical challenger. And it's quite simple. So the quantum adversary chooses two messages, sends them to the classical challenger, and the classical challenger is essentially a classical algorithm that flips a coin and encrypts one of those two messages, okay? Sends the result back to the quantum adversary, and note that this string now is just a classical string, and the adversary receives the string, maybe does some additional quantum computations, and then has to decide which message was encrypted, okay? So the adversary has to output a bit, and if B prime agrees with B, then we say the adversary won the game, okay? And this is a nice way to quantify indistinguishability. And we use the following definition. So we say that a scheme pi, say a symmetric key encryption scheme, has indistinguishable ciphertexts if essentially no adversary that is efficient and quantum can win at the following game with probability much better than 1/2, okay? So note that there's always an adversary that can win with probability 1/2 by just guessing at random, right? So we're saying that any advantage must be negligible. And n is, for example, the security parameter or the length of the key, say. Okay, but is this the only adversary you want to prepare for? Well, we know that crypto systems are typically not broken in this sense. Typically, the adversary has more information about a crypto system when the adversary actually breaks it, right? And one way to model it is to think of an adversary that has additional access to the crypto system. For example, an adversary that can learn something about encryptions or decryptions of the crypto system, okay? And one way to model it is, for example, a lunchtime attack, where, an adversary kind of tricks an honest party into encrypting or decrypting ciphertext for the adversary, or, the model where while everyone is having lunch, someone goes to the computer and encrypts or decrypts plaintext or ciphertext and thereby learns something about the crypto system. So now we'll consider such attacks. We call them lunchtime attacks. They're kind of standard attack models in classical crypto, and we'll kind of transfer them to the quantum case, okay? So now we'll look at the case, what if the quantum adversary has lunchtime access to encryption and decryption, okay? So this is now the realm of chosen ciphertext attacks. And let's look at the following game. Let's break it apart. So first, notice that there's, again, a challenge phase where the adversary has two messages. The challenger encrypts one of them, and sends it back to the adversary. And this is the same adversary, but all we're saying is we're kind of splitting this into 2 rounds, this game. And we're saying there's an adversary that doesn't know what the challenge looks like. We call this the adversary before the challenge. And then there's the adversary who actually has seen the challenge ciphertext and can do queries based on what this ciphertext is. Okay? So this is that. And then we assume that the adversary has kind of access to oracles for encryption and decryption that help the adversary win at this game. Okay? But now notice that we're looking at a definition in the quantum world, right? So we're assuming that these oracles here are actually quantum operations. And the adversary could, for example, instantiate a message register and get, as an output, a message register and an encryption of this message. And of course, this translates to superpositions by linearity. Okay? So why do we consider, as you might have noticed, there's decryption access only prior to the challenge. And this is just because we're kind of considering the weakest security notion that considers decryption access. And we just say, okay, we'll just look at decryption access prior to the challenge. We don't need adaptive queries where the adversary actually sees the challenge ciphertext and can then also decrypt. So we don't look at this model. We consider non-adaptive quantum chosen ciphertext attacks where decryption access is limited to the pre-challenge phase only. Okay? And then we define a security notion based on this. We're saying this game should be hard to win if the scheme is int QCCA1 secure. And this is just a short version of saying that it's secure under non-adaptive quantum chosen ciphertext attacks. Okay? And again, we're saying the probability of winning the game should be no better than the trivial adversary who just guesses at random. Okay, so now that we have this interesting security notion, can we actually find a scheme that is secure in this model? So we want to prove security, but we don't really have the tools to do that. We have to introduce a kind of proof technique to get there. And this is where quantum random access codes will become useful. So quantum random access codes were studied by Ambinus and others a few years ago. And basically the idea is, can we encode a large bit string into a small quantum state and then decode it? Okay? So maybe at first sight this is not unreasonable. You know, after all, qubits have this exponential power of storing all these amplitudes. You know, maybe it's possible to actually decode all this information in a small state. Okay, but bad news for Alice and the rabbit. So turns out that this is not a feasible way of communicating. So suppose that the message length is exponential and the quantum state is only of polynomial size. And then we can consider the average bias in decoding, say, a random bit of this message. And we can show that the average bias of decoding a random bit is actually negligible. So the advantage in doing this is ultimately infeasible once you increase the message length. Okay? And this will become really useful for security proofs because, as you might remember, we always assume that the quantum adversary is polynomially bounded. So there's only so much the adversary can actually put into a small quantum state and then later recover information from it. Okay? And we can use this for a security proof. And now we'll look at a scheme that actually satisfies our security definition. Okay, so this is a standard textbook security scheme based on pseudorandom functions. And here we actually require pseudorandom functions to be quantum secure. So what we mean is those are actually functions that look random to any quantum adversary. Okay? So what is a pseudorandom function? A pseudorandom function is a family of deterministic and efficiently computable functions. And we're saying that, you know, if the adversary were interacting with an oracle for either a pseudorandom function or a random function, the adversary would have no way of telling which oracle it's interacting with. Okay? And even if the adversary has quantum superposition access to actually evaluating this function. Okay, let's look at a symmetric key scheme that uses such a family of random-looking functions. So let's look at encryption. So if we want to encrypt a message, say an n-bit string, we sample a random string uniformly at random. So the dollar symbol means uniformly at random. And R is our random string. Okay, then we output R, the random string. We evaluate the random-looking function at R and add it into the message. So if the function looks random, then adding it into the message will make it look random. Right? So this is kind of a reasonable way of encrypting a message. And how can we decrypt? Well, if we can look at the randomness string, we can just evaluate the function there and then get rid of it again, right? We can add it back into the ciphertext. Okay, now let's look at a kind of high-level proof idea. So the proof is a bit more technical, but I'll just give you a kind of high-level idea of what's going on. So we're saying fix any efficient quantum adversary, And the first thing we do is we replace the random-looking pseudo-random function by a proper, perfectly random function, okay? And by the assumption that this function looks random, we know that this won't affect the success probability of the adversary in any way. And note that the adversary here is trying to attack this int QCCA1 security game. So remember, this is the game in which the adversary tries to distinguish which message was encrypted, and the adversary gets decryption and encryption, oracle access, and later only encryption access, okay? So the adversary here that we fix is playing this security game, and we're saying if you replace this function in the security game, then this doesn't really affect the advantage of the adversary, okay? And the final step of the proof, we're saying, okay, look, the adversary who's playing this indistinguishability game is essentially divided into two rounds. So we have the adversary before the challenge and after the challenge. And the adversary before the challenge has all this information by having access to encryption and decryption. And the adversary is generating a polynomial-sized state. And later the adversary is sending it to itself so that the adversary can recover information from this small quantum state, okay? So this looks kind of like a code, okay, that is, or like a transmission of a quantum state that should be decoded. And we're saying that you can actually use this adversary to construct a code from this, and then we can argue with our lemma that any advantage in decoding information from this code must be negligible. So why does this work? Well, look at this function. It has exponentially many input-output pairs that the adversary would have to know to win at the challenge of distinguishing messages. But the quantum state or the memory that the adversary has access to is only polynomial size, so ultimately the adversary cannot decode the information the adversary needs to win at the game, okay? So the real proof is a bit more technical, but on a high level, this is what happens. Okay, so this brings me to the last section. So now I'll talk about learning with errors in our security model. And Thomas already mentioned learning with errors in his talk. So what is learning with errors? Well, we use it as a kind of primary basis of hardness for post-quantum crypto systems. Okay, you can get a lot of interesting crypto out of it. You can use it for public key encryption, for fully homomorphic encryption, and you can even define quantum secure pseudo-random functions. Okay, so if you haven't seen this before, essentially learning with errors is the following problem. It's basically solving noisy linear equations modulo some integer. Okay, so on the left-hand side, you see these random coefficients. And on the right-hand side of the system of equations, you get the inner product between the coefficient vector and the solution vector. And then we add some noise to this result. So now the linear equations are actually noisy. Why do we do that? Well, if it weren't for the noise, this would be simple, right? We could just use Gaussian elimination and solve a system of equations. But because of the noise, we believe this is a hard problem. And we have good reasons to believe why it's hard. And it turns out that we actually also believe that it's hard against quantum computers, okay? So how can we use this for a crypto system? Well, let's look at the following simple crypto system. So this is about solving linear equations, right? And if Alice and Bob know the solution to these equations, they can communicate in the following way. So if Alice wants to encrypt 0, she just outputs a correct noisy linear equation that is approximately correct. And if Alice wants to encrypt 1, she just outputs an incorrect noisy linear equation that is definitely not correct, okay? So this kind of motivates the following scheme. So here we see if we want to encrypt a single bit, we just output a learning with errors equation. And depending on what bit we want to encrypt, after the error, we still add an additional shift, okay? So if you encrypt 0, then nothing happens and we just have a noisy equation. But if we encrypt B as being 1, then we make the equation incorrect by shifting it by Q/2, which makes the equation as incorrect as possible, right? And you can think of it in the following sense. So if the error is from a discrete Gaussian distribution, which it typically is, then if you're encrypting 0, you're using a Gaussian that is centered around 0. And if you're encrypting 1, you're using a Gaussian that is centered around Q/2. Okay? Now, in this talk, I'll show you a quantum attack on plain learning with errors encryption in our security model. Okay? So there are some caveats there that I'll talk about. But basically, our quantum algorithm uses a single quantum decryption. And it's quite easy to come up with a classical attack against this, assuming you have classical decryption access, okay? But we're saying if you had quantum decryption access, this attack would be much more devastating. And in fact, it turns out you only need a single quantum decryption query. Okay? What do I mean by quantum decryption query? Well, look at this decryption function there. Okay? This function is essentially just checking if an inner product is small, then it outputs 0, and if it's large, it outputs 1. Okay? So we're saying if you had quantum superposition access to such a decryption function, then you could break LWE encryption much faster than a classical algorithm. Okay? Now let's look at the quantum attack. So this attack turns out to be a variant of Bernstein-Vazirani, so a famous quantum algorithm, but it's a bit more technical and slightly different. And essentially, we have quantum access to a rounding function. Okay, let's look at the rounding function at the top of the slide. So notice that it's easy to see that decryption is kind of a special case of a linear rounding function that just computes the inner product of an input with the secret, and then checks, is the inner product small? Then we output 0. If it's large, we output 1. Okay? And at the top, you see what the oracle is. So we assume we have quantum oracle access to this decryption function. Okay? So here's how the algorithm works. It's quite simple. So in the first step, we prepare a uniform superposition over all possible values of x. And at the end of the algorithm, we're hoping to measure the secret of this linear rounding function with high probability. Okay, that's our goal. So we have this uniform superposition. We apply the oracle once. This will give us phase kickback, which means that the function is now computed into the phase of the superposition. And this will give a few minus signs, depending on whether the inner product with x is large or if it's small. Okay? In the final step of the algorithm, we apply the quantum Fourier transform. So this is the Fourier transform modulo q, which can be efficiently implemented. And let's look at the output state. So this is what happens once you apply the Fourier transform. And let's ignore the minus sign for a minute. So after we do the Fourier transform, we now have Fourier coefficients. So we're in the Fourier basis. And now we can ask the question, what is the amplitude that corresponds to measuring a fixed y, right? So if we ask what are the amplitudes for y, we have to sum over all these x's. And now we have to sum over roots of unity. These exponential factors there are roots of unity. And for a fixed y, they're kind of equally spaced around the unit circle. But there's one string for which something really funny happens. So if you ask, what if y is actually the secret string, then we have the linear rounding function actually determines if the inner product between x and s is large or small. Depending if it's large or small, we get a minus sign. And on the right-hand side, we have e, or root of unity, where we have the inner product between x and s. So there's a lot of nice symmetry, and what ends up happening is that the left-hand side of the roots of unity actually gets flipped to the right-hand side. And as you might remember, that the sum of all the roots of unity adds up to 0. But now we're actually not adding all of them up. We're adding half of them up twice. And this actually doesn't give 0. It gives a constant number. And it turns out the success probability of measuring the secret key is actually a constant factor. Okay? It turns out that the probability of measuring the secret key that our rounding function is using is actually 4 over pi squared. Okay? So in summary, once we have quantum decryption access, we're essentially dealing with a rounding function, and we can run this algorithm to measure the secret key with high probability. And as a consequence, we can recover the secret of learning with errors with high probability. Okay? So here's an overview of our results, at least the ones that I was talking about in my talk. And if there's one thing I want you to remember from this talk is that we should be careful in thinking that learning with errors is always as secure as it is, classically as secure as it is quantumly. Because, I mean, even if learning with errors is hard for quantum computers, we still saw a case where the security behaves very differently in the quantum case, okay? So we should be careful in thinking that no matter what the application is, that classical security is the same as quantum security, okay? We just gave an example of an attack, and admittedly, it's a very strong attack model. But nevertheless, it suggests that we should be careful about learning with errors encryption in any quantum setting. Okay, so this is it. Thanks.
Now talk is all from the discussion.